Okay, so that is all about centripetal acceleration and tangential acceleration. And now it's actually quite straightforward to talk about centripetal force. When we have circular motion, we often talk about a centripetal force associated with it. This is written as Fc is equal to mass times the centripetal acceleration, AC. And so F sub c is what we'll use to denote the centripetal acceleration. And we saw from a few slides back, we derived, in fact, that acceleration in the centripetal direction is v squared over r. So we just combine that with Newton's second law, right? Mass times acceleration. So now it becomes centripetal force is mass times v squared over r. Now, one thing to be clear about is that the centripetal force is not a new force. It's really just a relabeling or recharacterization of the existing force or forces. Right? So we've already studied several of these forces, like we had tension in a string, we had normal forces from a surface, we had like a force of friction, and forces like pushing and pulling forces. Right? Centripetal force is made up of one or more of those. So it's not a new force, it's just a recharacterization of the existing forces. It's the component of the existing forces on an object that points towards the center of the circular motion that the object is undergoing. Right? It can be a single force, or it can actually be a combination of forces. So for example, if we look at the example here, where we look at a mass at the end of a rope, and it's just rotating in some uniform circle, right? We've tied this mass to a string, and let's say somebody has kicked it, and this is like a frictionless surface, so it just goes round and round and round at constant speed. In this case, the centripetal force is supplied purely by the rope, right? It's really purely by the tension in the rope. That's the only force there is. There's no other forces pressing on it. This is a frictionless surface. Another example of a centripetal force that consists of just a single force is a lab centrifuge, or might be easier to picture it as if you've ever been to an amusement park and ridden one of these giant centrifuge type of rides where you stand up against the wall and the ride starts to spin around and around really fast, and you get pressed up against the wall. So here, the centripetal force is purely due to the center pointing normal force of the cylinder wall, right? Basically, as you ride this little kind of giant merry-go-round thing, your instantaneous velocity at any given point in time is such that you're moving tangential to the circle, so right here, he would want to fly off like this. If there was no wall here to hold him in, this person would just fly off in this direction. So the thing that stops him from flying off is the pressure of the wall, this wall pushing on his back. Right? And so that's a normal force of a surface keeping this object from passing through it. Right? And that's there's no tension. We can assume that the floor is even totally frictionless, totally polished, it'd be fine. It's really just the wall that keeps him from passing through and flying off of this thing. Okay. Centripetal force that is purely due to one force would be a car going around a turn on a flat road. Here, the centripetal force consists purely of the force of static friction between the road and the tires. It's basically that the tires would skid in a direction kind of perpendicular to the way they rotate, if it weren't for the friction of the road. So without sufficient friction, for example, if there were ice on the road, the car would be unable to make the turn and would instead skid out away from the center of the curve. So friction is the only force here that is keeping it from doing that, and it ends up pointing inwards towards the center of the circle. So we've seen that centripetal force can be just a single force, like the normal force on a merry-go-round ride, or a frictional force in the case of going around a turn on a car on a flat turn, or tension if you have something swinging around a horizontal circle on a rope. So for an example where the centripetal force is not a single force but actually a combination of forces, consider a race car like this Ferrari with me driving it, driving in a horizontal circle that's banked. So it's a tilted circular racetrack. Right? If you look at most racetracks, it's not flat. It kind of curves upward as you move towards the outside of the outside lanes. In that case, if we draw the normal forces and frictional forces here, we see that the normal force points not straight upwards, but kind of upwards at an angle because the road is banked. The frictional force, which, in this previous picture we had it perfectly horizontal. Right now, because the road is tilted, it points along the road because that's the, it of course has to be along the surface that's causing the friction, points slightly downward. Sorry about that. The end result is this is traveling in a giant circular track, and so the center of that track is in the horizontal plane here in the middle of the field, and so that's the centripetal force direction, right? Centripetal force points radially towards the center of the circle, but now both the frictional force and the normal force actually have a non-zero component in that direction. So the total centripetal force is actually made up of a combination of the radial component of the normal force and the radial component of the frictional force, and they both contribute. Example of calculating motion using these centripetal forces. So let's consider this example that we looked at just a few slides back of a car attempting to navigate a turn on a flat horizontal roadway. We'll say the radius of curvature of this turn is 50 meters. In other words, if we pretend that this was a portion of a large circle, then that circle would have a diameter of 100 meters and a radius, therefore, of 50. We want to know what the maximum speed is that the car can take the turn if the coefficient of friction, of static friction between the road and the tires is 0.8. So our strategy here is that first we note that the centripetal motion is provided purely by the force of friction. Without the friction, the car would not be able to make the turn. It would skid out, and it would move. In skidding, it would move away from this center of the circle. The other thing to note is that we're using the coefficient of static friction because we're looking for a solution where the wheels do not skid, and so that there's no actual motion away from the center of the horizontal circle. To use the kinetic coefficient of friction, we would have to be in a regime where the tires were already slipping and skidding across the surface, and we don't want that. Right. So for a solution, we always keep track of what our goal is. Our goal is to find the maximum speed of the car for which the centripetal force provided by the static friction the centripetal force required to keep the car moving in that circular turn, which is provided by the friction of the road, does not exceed the maximum available static frictional force. Right? And we saw a couple of slides back that, several slides back, that the maximum available static force is equal to the coefficient of static friction times the normal force. Right? So because we're dealing with centripetal forces and with static friction, it's clear that there are two relevant one too many relevance here. Two relevant tools would be the equations for both centripetal force and the equation for friction. All right, so here's the equation for centripetal force, it's mass times centripetal acceleration, mv squared over r. And here was our force for maximum static friction. Right? There should be kind of a comma max here. All right. So we have the maximum static coefficient, maximum static friction available, and the centripetal acceleration and force required to keep it on the road. Since from looking at the scenario, since there's no rope attaching this thing, there's no guardrail holding the car in, then the only source of centripetal acceleration is that static friction. So we can say that the centripetal force that we're trying to get is equal to the maximum centripetal force, that is the one at the maximum velocity that we can take this curve at, is equal to the maximum static friction that's available between these two surfaces. So if we can equate these two, because it's the one and only force providing centripetal force, then we can equate the right side of these two equations, and we get mv squared max is divided by r is equal to mu s n, coefficient of friction times the normal force, right? And we notice immediately, or we state next, that the normal force for a horizontal roadway has to perfectly equal and perfectly cancel the force of gravity, right? Because if it's a flat roadway, then gravity points straight down, and the car clearly does not fall through the road, so there must be a normal force pointing straight up, perpendicular to that horizontal road, that provides just enough force to counteract the gravitational force. So we can say that the normal force is just equal to mg, right? Finally, this gives us, if we plug in mg for the normal force, we get v max squared over r is equal to mu s times mg, and we immediately see now that the m's nicely cancel, and this becomes independent of the mass. We end up with an equation that tells us that v squared max is just equal to mu s mg times r. I'm sorry, mu s g times r, because this m already canceled that m. So v max is the square root of mu s gr. And finally, we can just go ahead and we plug in our numbers. We plug in for mu s, 0.8 for a dry road, 9.80 meters per second squared for the acceleration of gravity, and then the radius of curvature of this roadway is 50.0 meters. That gives us the square root of 392 meters squared per second squared, which finally works out to about 20 meters per second, or about 44 miles per hour. So a car taking a turn on dry asphalt on a flat roadway where the curve has a 50-meter radius can go no faster than about 44 miles per hour before it would skid out. Now, on the other hand, if that road were icy, so the coefficient of static friction were much less, a reasonable upper bound might be kind of 0.2 for mu s, then the maximum speed for navigating that flat turn would be greatly reduced, right? Because if we look here, we see that the maximum velocity goes as the square root of all these factors. Then it also clearly goes as the square root of the coefficient of friction. So if we drop the coefficient of friction from 0.8 to 0.4, which is a factor of 4, then the velocity, the maximum safe velocity, would go down by a factor of square root of 4 or a factor of 2. And so we would find that the maximum velocity that you could take this turn on when the coefficient of friction for the icy surface is 0.2 drops to 22 miles per hour, or 9.9 meters per second. All right, I think that's all I can manage for tonight. And I will see you guys on Monday. Thanks, and sorry for the inconvenience.